Hi, so thank you very much. Yeah, as he said, this is actually work I performed in 2013, so it's been a few years. For the past few years, I've been concentrating on my startup. So answer extraction is kind of the central, or one of the central parts of question answering. The problem is, given a question and a sentence with relevant information, how do you get the relevant information out? So for example, you could have the sentence, James Hervey, English divine, was born at Hardingston near Northampton and was educated at the Grammar School of Northampton and at Lincoln College, Oxford. And the question, where did James Hervey attend school as a boy? And we want to get the answer, the Grammar School of Northampton, out of this. So even though all of the information is right there, there's still work to be done. And arguably that work is the task of understanding the sentence that was just read. So unfortunately, in 2013, there were a few evaluation sets for question answering, but it was really hard to find a data set to learn question answering from. Kind of the standard evaluation data set was the NIST text retrieval conferences. But the problem with using these for learning is that the supporting sentences were mostly unlabeled, or they were labeled only for submissions by the competing systems. So there was really no good way to tell whether a sentence that contained the right substring was good for training. So you might have like a question, who was Abraham Lincoln's Secretary of State? And of course, the answer key would tell you it's William Seward. But when you encounter an instance of William Seward in the text, you don't know whether the information that supports the fact that he's Secretary of State is right there or not. And that's a problem. There was another kind of evaluation data set that was not against large corpora, but against particular documents, which were known as reading comprehension tests. Remedia corpus was one of these. Generally, the data sets were not large enough for training. Remedia was like on the order of 600 questions, 120 stories, and background knowledge could be required. So how did people manage to do question answering without actually learning question answering? Well, a typical approach was somehow to measure the similarity between the syntax of the question and the supporting sentence, and then try to do an extraction where the alignment was best. Or another approach was to map the question into an established question type that corresponded to a relation that the machine had learned to recognize. But unfortunately, labeled data for recognizing relations is scarce too. The standard distance supervision hypothesis, say if you had a database of state capitals, would have you assume that each sentence that mentioned both Albany and New York would actually imply that Albany is the capital of New York. And a study by Riedel in 2010 found that this assumption was violated as much as 31% of the time. So what we want to do in this work is to somehow abolish question types to be able to flexibly answer arbitrary questions. We want to create a better data set for learning answer extraction. And we want to learn how to compare a question and a support sentence and find an answer. Our basic tool for this is going to be word embeddings, but we need to learn how to compose word representations into sentence representations and how to follow the parts of the sentence that are relevant. So we address all three challenges and actually learn how to answer questions. So the data set that we develop is called TurkQA. It's based on the first sentences of Wikipedia articles used as support sentences. Because we always took the first sentence of the article, we mostly did not need co-reference resolution, and there was lots of information in one sentence. And with this, we had a mechanical Turk write 4 questions that were answered within the given sentence. They could be short answer or yes or no. The short answers were supposed to be non-overlapping substrings of the support sentence, and there were supposed to be no more than 2 yes or no questions per support. So with this data set, we were hoping to learn which syntax within the supporting sentence was addressing which questions. So in this way, we collected 13,424 problem sets and almost 40,000 questions of short answer type. More than 600 workers contributed. We did a spot check to see whether these were error-free or not, and we found that more than 96% of the problem sets were error-free and more like 99% on a question basis. To ensure that these submissions were actually useful for training, we required that there be no pronouns in the questions. All the words had to come from the dictionary or from a supporting sentence. And the answers were not allowed to overlap, and we set the guideline that any English speaker should be able to answer the question using the supporting sentence only without background knowledge. So here's an example of one of the question support answer triples that we collected in this way. And you can see that we've basically made the question answering task into a sequential tagging problem. And this diagram gives a hint as to how we're going to solve it by classifying the gray nodes in this parse tree as things that we want to follow. So to back up and to say what our strategy is to parse the question in the support sentence, to use distributed word representations to embed every word into a continuous feature space, use autoencoder neural networks to derive representations of the internal parse tree nodes given the word vectors, and finally to take the representation of the question and recursively descend the parse tree of the supporting sentence to decide which nodes or words to extract as the answer.
So Christopher,
yeah.
So I thought in the previous slide you said that the answer may not be from the sentence, but now the strategy only would work for words from the same sentence. Yeah.
That's right. Or part of that's right. So in the TurkQA task, the short answers had to be actually substrings within the support sentence. So this is different from like MS Marco, where you can have short answers that that are not anywhere in the supporting material. So because of this, it's just a tagging problem. So our distributed word representations come from a system called SENA, the Semantic Extraction Neural Network Architecture, developed by Colabert et al. In 2011. This gives us 50-dimensional dense feature vectors for every word, and they're co-trained on the semi-supervised task of learning to rank valid English sentences ahead of invalid ones, which you can think of as a kind of language modeling, and on the supervised tasks of part of speech tagging, named entity recognition, chunking, and semantic role labeling. The system trained for about 7 weeks on the Wikipedia and Reuters data set, and the dictionary size was slowly increased from 5,000 words to 130,000 words using curriculum learning. These vectors seem useful because they can solve syntactic tasks like those, and also because similar words are neighbors in the embedding space. So this gives us vectors for most of the words that we're going to encounter, but we have to apply a trick to deal with words that are outside of our dictionary. Typically, those words are mapped to one fixed vector by the language model, but instead we're going to extend the language model vector by a random vector that's unique for each word, so that the extended unknown word vector would match other occurrences of the same word, but not match other unknown words. And we have fixed distinct extensions for all words in the original dictionary. So to take word representations and put them together in the higher levels of the parse tree, we use autoencoders. An autoencoder is a neural network with 2 parts, an encoder half and a decoder half, where the encoder half squishes 2 vectors into a single vector, and the decoder produces 2 vectors from a single vector. And the objective of training is that when you apply these two in composition, you should get very close in distance to your original 2 vectors. So that's the idea, but there have been some concerns about using autoencoders in real-world tasks. One of them is whether information is lost after repeated recursion. Another is whether low reconstruction error is enough to keep the information needed for classification. A couple of approaches to these problems have been deep unfolding recursive autoencoders, which in recursive application penalize you for the reconstruction errors, not just at one level, but many levels down a tree. And a co-training approach for sentence classification and sentiment analysis. So we're also going to introduce a co-training problem. Our co-training problem is subtree recognition, which basically means that our vectors can tell what information lies below them. We co-train the autoencoder to classify node pairs so that it tells us whether node X is an ancestor of node Y. So for the blue-green pair, the answer would be yes, and the blue-red pair, it should predict no. So with these autoencoders, we now get features at every level of the parse tree. Actually, our word feature vectors are not just the word embeddings, which are 50-dimensional, but they also contain these capitalization features, named entity features, and part of speech tagging features, each of them represented by a lookup table. And then we leave 200 dimensions of 0 padding in the word vectors, so that as we go up the parse tree, there's more capacity left that we haven't used yet. And the autoencoders don't just take the pair of words, actually. They take the pair of nodes and the node type of the node we're combining into, like noun phrase or verb phrase, so that they're able to reconstruct not just the 2 children, but the type of the node as well. So with those features defined, we can apply our recursive parse tree descent procedure, which is to start at the root of the parse tree of a support sentence, and for each child, decide whether to follow it given the question vector, the current nodes vector, and siblings around the current node, 2 on either side. I'm sorry, this should say the parent node vector. So for example, when we're going down this parse tree that we used in our example earlier to find this death date, when we're at the step of classifying the noun phrase node, node number 33, we're looking at this boxed frame of consisting of the 2 siblings before it, so the previous noun phrase, which is the birth date at node 32, and then a literal dash, and then the vector for this noun phrase itself. Each of those gets paired with the question vector and the parent representation at node 40. And there are not more siblings to the right of this node, so we fill those in with zeros. And this information is given to our classifier, which is just a convolutional neural network. A convolutional neural network produces a sequence of output vectors from a sequence of input vectors, where each output depends on a sliding window of adjacent inputs. Here we're going through in sequence each level of the parse tree and taking those siblings as the sequence as input to the network. A little bit more about the architecture. We have one hidden convolutional layer of dimension 30. We have a hyperbolic tangent as our nonlinearity, and we have a linear output layer. And we train the system by stochastic gradient descent, recursively following any node for which the prediction is affirmative. So it's not fatal to classify additional nodes in the interior of the parse tree as positive, as long as we stop somewhere before picking up wrong terminal nodes, but we still penalize that. So compared to like using path-based features in a logistic regression classifier, here the ordering of the siblings is visible to the classifier, and so this makes it useful for picking up birth dates or death dates which otherwise have isomorphic paths to the rest of the sentence. So with this system, we ran an experiment on our TurkQA dataset. We disregarded the yes/no questions, and for training, we had about 38,000 questions, and for testing, almost 1,500 questions. And we evaluated the system in two settings. One of them was a short answer setting, in which we just looked at the token classification error rate, and the other was a multiple choice setting, where we took each short answer in the problem set, in other words, the answers to the other questions. We took those as the choices. We averaged the classifier output over the tokens in each of those answers, and we chose the answer with the highest average, skipping the question if none of the answers got a positive average.
So I'm not sure what you mean by the answers to other questions.
So remember, in these problem sets, a Turk is writing 4 questions about a single sentence. So there are generally 3 other questions to look at, and all of those had to have non-overlapping substrings as answers. So as a baseline, we took about the only open source system we could find, which was a Carnegie Mellon project called OpenEphra. This evolved from their Trek submissions. But we bypassed its retrieval module to automatically use the support sentence instead of doing a live web search like it normally does. And here are results, both in terms of short answer and multiple choice. So on a short answer basis, you see that the main system beats OpenEphra by quite a lot, 0.37 to 0.209, but a much narrower gap on a multiple choice basis, which suggests that OpenEphra is getting a piece of each answer, but that maybe its question types cannot extract the kinds of answer boundaries that the Turks set in their questions. You can also see the contribution of our various techniques to the system. So if you try to do this with vanilla autoencoders instead of the autoencoders that were co-trained for subtree recognition, you go down to 0.269 in F1 instead of 0.37, so more than 0.1 difference. If you try to do this without the special representations for unknown words, you get 0.305 instead of 0.37 in short answer F1. And getting a lot of data also was pretty critical to this system. If we had stopped after on the order of 1,000 questions for training, we can only get 0.236 in our F1 score.
So when you don't use subtree encoding,
yeah,
how do you handle the variant, the different number of words in different sentences? How do you do the encoding and decoding without tree?
You still have an autoencoder. You just don't have one that was co-trained in that way.
And the autoencoder is structured in how?
The autoencoder takes, or are you asking if there are more than 2 children?
So in one sentence you have like 3 words, and in another you have 10 words.
Right.
How does the autoencoder handle different lengths?
So it's not combining adjacent words. It's following the structure of the parse tree. So you could have a noun phrase with like 3 children, and we actually binarize the parse tree so that it only has to combine 2 vectors at a time.
So that's the main way, but without substring, without subtrees, how do you do this? I thought the second line in the table was not using the tree at all.
No, it uses the tree. It uses the same technique basically. The only difference is the training objective is pure reconstruction error. So here are some qualitative examples of the system's output. So here's a question: what was Robert Person's profession? Baseball pitcher, and the system gets it exactly. Maybe it kind of stems professional somehow in the language model, I don't know. But it's a good result. What is the name of the British charity based in Haringey in North London? We get this as exposure exactly correct. This one was easier because there's a lot of overlap between the question syntax and the support syntax. Where is the Arwa group? Here the Turk chose the Chamoli state of Uttarakhand state. And the system actually found a more complete answer. It found Chamoli district, Uttarakhand state, northern India, but it got penalized for including northern India because the Turk didn't have it. On the other hand, it didn't have the or of, and it was also penalized for that. So this is perfect on a multiple choice basis, but it loses some points in short answer. Here's another example. What genre was Lights Out? Lights Out was an extremely popular American old-time radio program, an early example of a network series devoted mostly to horror and the supernatural, reading suspense and inner sanctum. The Turk chose horror and the supernatural, and we got horror supernatural. This is impressive because genre doesn't really exist anywhere in the supporting sentence, and so it seems that the language model somehow must know the relationship between horror and the word genre. Yeah?
Do you have a sense of why your system is leaving out these function words?
Yeah. I think it's because it can't see the decisions made at higher levels. So if you just have some connective words like and or whatever, at the bottom level, it can't tell that that's very important, even if it knew above that it wanted to take a whole noun phrase. It might take the noun phrase for A and B, and then it sees that A is important and chooses A, and it sees that B is important and chooses B, but forgets that it would be nice to have and in between. And a technique like pointer networks or something, it can do better on that. Yeah?
You could presumably evaluate it on the closure of the answer, right? I mean, if you have horror supernatural, you just take the subspan that starts at horror and ends at supernatural in the paragraph.
Yeah, you could join all the words that were tagged together.
The evaluation of it all? I mean, would it help the evaluation of it?
I think the system would perform better with that kind of approach. So we developed the TurkQA dataset in the belief that for computers to have a complete knowledge representation of a sentence, they should be able to answer all of the questions that a human can ask about it. But there are some aspects of question answering that we haven't addressed here. And these are mainly the ones in Facebook's 20 baby data sets. So they include things like basic deduction. Jessica's a cat, cats eat mice, what does Jessica eat? Our technique is not really built for this. Temporal reasoning, spatial reasoning, and counting. Also, in the years after our work, there were finally some other big data sets that were suitable for learning question answering that were released. One of the best ones is Squad, which has 23,215 paragraphs from over 500 Wikipedia articles and 5 questions per paragraph by crowdsourcing, and they're answered by substrings of a paragraph. So on the surface, this is very similar to the data set we've developed. Actually, it has almost 3 times as many questions. But on the other hand, the machine now has to determine which sentence has the answer, and the questions can have pronouns and test co-reference. So our system cannot deal with co-reference, we're pretty sure. So evaluating it on Squad would be partly a matter of luck to see how the co-reference came out. So if you have a system that can do these things, this is a better set to use. If not, maybe you want to evaluate your system on a narrower task like TurkQA. Another data set that came out last year was the MS Marco set, which is built around 100,000 queries from Bing. Actually, not all of these queries are in the form of a question. They took 10 extracts from web search results as supporting information, and they acquired short answers for each of the queries by crowdsourcing. But because these were not actually substrings of the original support, you need to grade the results using a metric like Rougeal or Blue1. And actually, when Microsoft trained their own system, they ended up turning it back into the substring classification problem by taking the span in the support with the highest Rougeal against the reference answer. So compared to TurkQA, the questions might be more natural with less back formation because they start with the queries instead of starting with the supports. It presents the same complications for the system as Squad, plus there can be answers that are not substrings. And of course, with these later data sets that are big enough for learning question answering, there have been systems such as this one done at the Malon Institute, bidirectional attention flow for machine comprehension, that do learn to answer questions. And this takes a very different approach both to how context is represented and how you check compatibility between a question and context. So for the context representations, it uses LSTM instead of autoencoders, and it views sentences as token sequences rather than as parse trees. And to compare question and context, the attention networks compare all pairs of question tokens and support tokens, whereas once we have the root question representation, we just apply that token by token to the context. So in summary, we've constructed a closely supervised question answering data set that we can directly train on. Our recursive parse tree descent procedure has brought us freedom from hand-designed features such as word distance or parse tree paths, and from question and answer types. We found that context representations are critical to the performance, as we see in the difference in score between our system with just a plain autoencoder and the special autoencoder with subtree recognition. And future challenges for our system would be to add irrelevant sentences, to link information among co-referent entities, and to deal with logic, temporal, and spatial relations. So thank you very much.